invitation and the opportunity to talk here. I feel very honored. So what I would like, syzygies in geometry. So this is a topic which is to my heart for a long time. So to quote my teacher, David, given a system of equation, it can be extremely difficult to analyze its qualitative properties, such as the geometry of the corresponding variety. The theory of syzygy offers a microscope for looking at the system of equation and helps to make their subtle property visible. So today I report on a joint paper with David, which was posted at the Journal of the MNS. So to give you an idea what you have to suffer through, first is syzygies, Hilbert polynomial, Betti tables. Then I talk about the geometry of syzygies as a side. And then I come to the real topic of the talk, the Boris-Söderberg's conjecture, of which I will then outline a proof further on. So cohomology of vector bundles. We somehow give a nearly complete classification what the cohomology table of vector bundles can be. I will be more precise later on. And then we have a positivity result, existence theorems, and generalizations. So a syzygy, given a ring R and a module M and elements in the module F1 up to Fr, a syzygy between the Fi's is just a linear combination which is 0. Or in other words, the vector G1 up to Gr is an element in the kernel of the map from the free module to M, which sends the ith generator to Fi. So kernel of phi is called the syzygy module of these elements. So let's start with an example out of Hilbert's famous 1890 paper, where he proved the syzygy theorem. So this is an example from the very beginning. So we take the rational normal curve of degree 3, the twisted cubic, and look at its equation. And you all know the equation. There are three equations, x1 squared minus x0, x2. That's true because, well, if you plug in the stuff, that's true. Now, we have three equations, but something of codimension 2, which means that we should somehow have interesting relations among f1, f2, f3. And indeed, the columns of these vectors, of this matrix, are syzygies. So, for example, x2 times the first equation minus x1, the second equation, plus x0, the last equation, is 0. So let's see the x2 minus x1 square term. First in the first cancels against this one in the second, and so on. So similar for the second column. And it's actually true that the syzygy module, all the syzygies are generated by the column vectors of this matrix. And as I said before, the fact that we have non-trivial syzygies, so we always have a syzygy if we have an ideal of the time fi times fj minus fj times fi, that's trivially 0. So we have always causal syzygies. The fact that we have also non-causal syzygy reflects that the number of equations is larger than the codimension. 4 points in the plane. So if we have 4 general points, the ideal, homogeneous ideal is generated by 2 quadrics, and we only have the causal syzygy. However, if 3 of the points lie in a line, it's the black line, then the quadrics have this black line as a common factor, and we have a common syzygy. So somehow the fact that we have a linear syzygy among these 2 quadrics tells us that the split of a factor, and that tells us that 3 of the points lie on a line. Hilbert introduced syzygies to define the Hilbert polynomial. So first the Hilbert function, if we have a graded module, then we can associate it to an integer k, the dimension of m in degree k. And the Hilbert series is a corresponding generating function. So then Hilbert's goal, Hilbert's application of syzygies were to prove that there exists a polynomial which for large values coincide with the Hilbert function. So I start really slow and prove this for you up to the syzygy theorem. So if you have a graded polynomial ring, variables x0 up to xn, a graded module, say given by a presentation, then we can compute a finite free resolution of at length at most n plus 1. We can continue this presentation to a free resolution where n plus 1 is the number of variables. And we can use this to compute the dimension of nk. The degree k part of this free resolution is an exact sequence of finite dimensional vector spaces, so we can compute the dimension of nk out of this sequence. However, to do so, it's we have to give each generator, certainly we will take only homogeneous generators in each step, so we should give each generator fi of fi a degree. So if beta ij denotes a number of generators of fi in degree j, then fi is the direct sum of s minus j, beta ij, the minus j, y minus j, not plus j. Well, that's convention. Is it Grothendieck? No. Must be, no. O of 1 should be positive. O of minus 1 should have no section. That's the basic reason. Yes. So the exact sequence, we can compute the Hilbert function. And then, since fi is a direct sum, we can have only to compute the number of polynomial elements of s minus j in degree k. Of course, that's a binomial coefficient. And now, in this binomial coefficient, we can regard the k as a variable t. So instead of a binomial coefficient, we take this polynomial of degree t, and then we see that the polynomial pm of t, hm of k is equal to pm of k for large values of k. This Hilbert series, this formula for the Hilbert function also proves that the Hilbert series is a rational function because, well, it's a rational function for the Hilbert series. The Hilbert series of the polynomial ring is a rational function, as you will know. Let's talk about the basic facts about the Hilbert polynomial. First, the degree of the Hilbert polynomial. If you have a ring A, S mod F1 up to Fl, and X is the corresponding variety in projective space, then the degree of the Hilbert polynomial is the dimension of X, and this is the dimension of this ring minus 1. The degree of X is R factorial times the leading coefficient of A, T, and that is also multiplicity of MA. We can also write the multiplicity of MA by taking the Hilbert series and cancelling as much as possible. So a co-prime rational presentation of the Hilbert series will only have 1 minus z to the r plus 1 in the numerator. And particularly we see that if the original expression for the Hilbert series will the numerator, the term above is the numerator, I hope, vanishes at z equal 1 to the order c equal codimension of x. So what is this polynomial? Took sort of a couple of years to really figure out what it is. What it really is, of course, is if we have a graded model, we take the associated coherent sheaf, and then the Hilbert polynomial really is the Euler characteristic of the f twisted by O of k for all k. And the last thing which one has to know about, if you have a family of sheaves f tau is flat, meaning it varies continuously in the sense of algebraic geometry, if the coefficients of the Hilbert polynomial are constant as functions of tau. So the graded Betti numbers, let's come to this. The coefficients of the Hilbert polynomial are the fundamental numerical invariants. The graded Betti numbers, beta ij, of a minimal resolution are finite numerical invariants. Minimal means that at each step we choose a minimal homogeneous generating set, which has as consequence that the image of the i's fi plus 1 lies in the maximal ideal times fi, or that the beta ij are some dimension of Tor groups. So they are invariants. I'm going to work a lot with tables. So I will try to explain how these tables are organized. So we had this resolution of 4 points in the plane. We have 2 quadrics, so 2 generators in degree 2, so we have s2 to the minus 2, and there was one Cauchy relation among them. And similarly, we had sort of one where there was a linear relation among the quadrics, so this is then a total degree minus 3. And the free resolution looks like that. So the way I try to memorize this table, if I have 2 numbers in a line, this corresponds to a linear map. If I have 2 numbers in a square, this corresponds to quadratic entries. In general, the Betti table is organized as follows. I have a different notation than in the previous talks. It's sort of rather reasonable, maybe not to have these. I mean, why should I name this d plus 1 if it lies in the d's column, d's row in first column? So I go for total degree. There's no reason to do that. But that's the way I was brought up with, and I stick to it. So the Betti table of the twisted cubic, 3 equations of degree 2, 2 linear relations should look like that, and this table encodes a complex of this type. All right. I have to say a little bit about the geometry of syzygies. So the Betti table of a smooth canonically embedded curve, C, of genus 7 is, so it sits in P6, and the canonical embedding is one of the following. So these are the only 3 possibilities. We have a smooth canonical curve, and they have a nice geometric interpretation. We need cubics in the idea, if and only if the curve is generated, if it's trigonal by Petri's famous theorem, and then sort of if we need causal relation, if you need syzygies up here, if the Clifford index is 2, then we have it if here's something, so we have 2 zeros here, then the Clifford index is 2, which means that we should have a linear system of Clifford index 2. So 6 minus 2 times 2 is 2. That's all right. So we have a G26. We also can have, of course, only a G14 or orthogonal curve. And then we have the generic case. And that's true in characteristic none equal to 0. So what kind of tables can occur is quite subtle. I think there's no big reason a priori to think that this number 9 couldn't be 8. Let me point out this 3. How does the 3 appear? So if we have a G14, then we have a scroll, and the scroll has resolution 1, 6, 8, 3. So a single G14 gives us 3 syzygies. If we have a G26, which most of the time will be a plane curve with, of degree 6, so it will be birational map, then this model of degree 6 has arithmetic genus 10, so there should be 3 nodes. So projection from each of the nodes gives us a G14, and 9 is 3 times 3. Of course, these G14s can come together, and the story is more complicated like that. Anyway, we would love to know such a thing in general, but we are very far away from that. Yeah, that's right. Gorenstein is the length. We see the length, so this is sort of easy, very easy. The length, the 3 regularities, so this is a regularity. The symmetry comes from Gorenstein, the length from Cohn-Macaulay. So here is the conjecture which started Boy and Söderberg in their marvelous approach to Betti tables. So Hunicke and Srinivasan conjectured that if we can estimate the multiplicity of an algebra just by the degree range of the beta ij's. So suppose beta ij is non-zero only in a range from d lower I up to d upper I, then the conjecture said that the multiplicity is bounded by the product of the di's, lower i's, and product of the upper i's. Well, there's factor 1 over c factorial.
I think one of those bounds involves tensor.
That's right. Yeah, I should. If we have a pure resolution, which means that we only have 1 degree in each step, then the bounds left and right are sharp. And the degrees which we have, the twists which we have, determine the beta i's, beta I di, completely up to a common factor. So, and if M moreover would be an algebra, so beta 0 would be 1 and d0 would be 0, then the multiplicity conjecture left and right coincide, and we can compute the multiplicity using this formula. Of course, this was the starting point to have an idea about the multiplicity in terms of the range. So here's the proof. The numerator of the Hilbert series looks, in this case, it simplifies, is the sum over minus 1 to the I beta I d to the zi, vanishes to order c at z equal 1. So this gives c plus 1 equations. No, c equations for c plus 1 numbers. So they're determined up to a common factor. If you think about the system of equations, it's sort of a fundamental type of equation. They're really independent. Let me give you some examples of pure Betti tables. So I have the twists 0, 2, 3, 5, 6, 8. So a quadratic step, a linear step. The difference is 1, a quadratic step, linear, quadratic. Then this is the smallest possible solution of this linear system of equation for the beta I. And similar here, that's also the smallest possible integral solution, because the numbers here are coprime.
Who's this the second thing? Who's this the second thing? What's the somewhat variety?
It's not variety, it's a module. It has 5 generators. The dual module has 3 generators. It's just a module. Whatever that is, it's a module.
Just
Yeah. So in their attempt to prove the multiplicity conjecture, Boy and Söderberg made a big step forward towards an answer to the fundamental question, which Betti tables are possible. So it's a very simple observation which gets them started. We can think of the Betti table as an element in a vector space. I mean, we have a table of numbers, we can add tables of numbers. And if we have a direct sum of modules, the Betti tables will be, the resolution will be the direct sum, so the Betti tables will be the sum of this. So it's rather natural, never occurred to me, to consider the convex cone spanned by all these possible Betti tables. So what Boy and Söderberg did, they formulated a conjecture which completely describes this cone. So up to a multiple, so we just have this cone, this rational cone. So we don't know about the integral points in which of these in the cone, which integral points actually belong to actual modules, but in some sense we know all kinds of inequalities between possible Betti tables, sums of linear inequalities between sums of Betti numbers. So here's a description of their conjecture. First, the existence for every degree sequence, there exists a Cohen-Macaulay module with a pure resolution of that degree sequence. The second is the cone of Betti tables is generated by the tables of these pure resolutions. So they form the rays in the cone. And then it's even better, there's a decomposition. Each Betti table has a unique positive rational linear combination of pure Betti tables. That there's some linear combination of pure Betti tables is clear by 2, if we believe 2. But here it's unique. In a unique chain, if we restrict to a unique chain of degree sequences. So the degree sequences are naturally partially ordered. If the entries are, if di is less than ei, then the degree sequences for all I. So there's a unique decomposition.
So first one, for every degree sequence, there is some.
Yes. Yes. And then they form the rays of the cone. And moreover, this cone has a decomposition, as you will see, into cells. It will be a simplicial, will be a union of simplicial cones. And okay. So, of course, Boy-Söderberg formulated this conjecture because it would imply the multiplicity conjecture. Another remark I would like to make, we can, since we are looking at Cohen-Macaulay module, we can immediately go to the case that the dimension of M is equal to 0, because we can divide out non-zero divisors of degree 1, and the Betti numbers don't change. So let's talk about dimension 0 modules. I tried to do the decomposition. We had a bunch of Betti tables of this type before, Bx, x could be a number. So we had 0, 3, 9 at least. So how to decompose this? So it's clear that only this diagram A and its dual and the B0 can contribute to this object. Because, yeah, it should be a sum of such things, rational sum of such things, positive rational sum. And it's also clear that only the 90 can contribute to the red X up here, right? So X divided by 16 is less than equal to 90 divided by 128. So we have a rational multiple of this inside. So the ratio of this we have it. So we have a bound on the x divided by 16. So this means that x is at most 11.25. So, and if we look, for example, at B11, it is indeed the sum of these three tables with these rational coefficients. I don't believe that this diagram B11 actually occurs, because it didn't occur for curves, for smooth curves. That's not a very good reason, but anyway, I believe nevertheless that it doesn't occur. One can see this already in easy examples. For example, for the degree sequence 0, 1, 3, 4, the numerically smallest possible Betti numbers would be 1, 2, 2, 1. But of course this is impossible because we have here two linear forms and then there would be causal syzygies up here. So this is not a possible Betti table. But twice of it can be realized actually if you take a generic 2x4 matrix in enough variables, it has a resolution like that. What we really would like to know, of course, is the monoid of actual Betti tables. That is a more difficult question. For one thing, it also depends on the characteristic of the ground field. So this diagram here doesn't occur in characteristic 2. If you have characteristic 2, then we have at least a 1 over here, which in particularly means that the analog of Green's conjecture in characteristic 2, if you know what that means, isn't true in that case. Let's talk about the fan structure. So I would like to have a bounded range. So let's say beta ij is only non-zero for j between lower di and j between d lower I and d upper I. Then within this range, every maximal chain of degree sequences has the same number of elements, namely b. Hence, the rays corresponding to any chain span a cone over a b-1 simplex. So the bounded Boy-Söderberg fans are equidimensional. So we have lots of simplicial cones and they're glued sort of in a complicated way. Now, to prove the conjecture, it's natural to look at the outer facets. So when do we get an outer facet? Well, first we get a facet of a simplex if you remove a vertex. Then we have the opposite facet. Now, since we're looking at a simplex which is a chain, we have one degree sequence f minus, which is immediately before, f, and then f plus, which is immediately after. So it turns out that the essential facets, the essential outer facets, have the property that f minus, f, and f plus differ only in two consecutive positions in which f plus and f minus have a linear step and f has a quadratic step. And, which is very nice, which makes it easier, this reporting hyperplane depends only on f minus, f, and f plus. So by Söderberg proved that for us. So I give you an example. I take 2 degree sequences which are hopefully complicated enough that we do see all phenomena. So So here's two linear steps and here's a quadratic step. I mark in the to come Betti table the position where I should to put numbers. So star I put where both are so all three sequences are non-zero, and plus and minus where the first or the second the f minus or f plus are non-zero. So this is now correspond to our outer facet, and I would like to compute the equation of this outer facet, because so the computation of the upper facet equation. So first I start out to put zeros below in every position greater than f plus, so here below, so where the 0 stars and the 0 pluses, in everything below. And then I look at the position where f minus lives, and I know, and I try to compute now the coefficients. I know that the dot product of this table with, for example, the complex of f minus has to go to 0. So since only these are all 0, only two numbers survive, so the ratio between these two numbers up to the sign is the same as the ratio of the corresponding Betti numbers of an f minus pure complex. So, and then I have to decide which sign I take, and since the dot product with f should be positive, here should be plus, then there must be minus. And now I can slowly go up. For example, to get the 60, I look at the complex which passes through the 60s, and all the other are sort of the known values. I just go once in one position up. So then I have the dot product with a complex which is above, is below f minus, and it's 0. So and only this number is not known, so I can compute this number recursively. There was no particular reason to go for f greater equal to plus. You could have also done f, put zeros upstairs and non-zero term downstairs. So there's actually more than one equation for the facet, which is completely plausible because we have these relations coming from the condition that the dimension of m is equal to 0. So the Hilbert polynomial of m, for example, is 0, and that gives us a lot of linear equations. So the lower equation will also have numbers. You see a little bit of pattern. For example, on the diagonal there seem to be always the same numbers up to sign. And that is actually completely plausible, because if I would compute the lower equation and take the difference of these two equations, that should be 0 on my complexes. So it should be given by the condition that the Hilbert polynomial is 0. And if you compute the Hilbert polynomial at a specific space in this, you sort of basically compute along diagonals. So the equations obtained from the Hilbert polynomial, being 0 in several positions, really all have this diagonal type. So this explains all zeros. So since I have zeros here and the diagonals are constant, I must have zeros here. So all the zeros are explained. It also gives a hint how to prove this result. Namely, the difference between upside, the lower and upper equation is really a sum of values of Hilbert polynomial of f with some coefficients. And if you think about this, well, it's rather natural to interpret this sum as a free complex tensorized with M. So let's look at such a free complex. So we have a free complex. We can sheafify it and get a vector bundle. So let's talk about cohomology tables. So let E be a coherent sheaf on Pn, for example, a vector bundle. Then we have the cohomology groups, and we can speak about the cohomology table. They are now sort of an infinite product. A vector bundle E has natural cohomology if for each twist K at most one of the groups is non-zero. It has supernatural if in addition the Hilbert polynomial has integral roots or distinct. So Z1 up to Zn in case of a vector bundle. So here's an example. If we look at the cohomology table of a supernatural rank 3 vector bundle in P3 with roots 3, -1, -4, then the dimension of these groups H, I, E, K minus I, so the minus I is natural if you think in terms of Castelnuovo-Mumford regularity, as indicated. So here are the terms on the diagonal are the terms which sort of add up alternatingly to the Euler characteristic. So these are the zeros of the Hilbert polynomial. And in every other diagonal there's at most one term. It turns out that also in each column there's only one term. And they're sort of so slightly decreasing. So the crucial idea is to consider the pairing between a Betti table and a cohomology table. So we take this sum. There's some minus signs. We sum k and minus k. That makes sense. That sort of makes these terms sort of happen in some degree, I guess. And then, of course, we can abbreviate these things. If we have a module and a vector bundle or sheaf, then, of course, we can, instead of M, we can put F, or the Betti table of F and gamma v. So here is our main result. F any free resolution of an S module and E any vector bundle, then this pairing Fe is non-negative. Moreover, under some condition on the regularity, it's actually 0. So the second part we will use to identify a suitable version of this as a facet equation later on. So we need enough vanishing for that. So it's not so obvious, I guess, that this is true because we have these alternating, we have signs. Without the signs, I guess the positivity would be easier. So for a suitable vector bundle E, the theorem gives a linear form with coefficients as indicated. They're not quite what we want. So we wanted these red things to go away. We want the table without the red things. And, well, we throw them away. So we have a homological degree tau. We have an internal degree C. And then we sum over only some of these pieces as before. And it turns out that these truncated functional, depending on tau and C, is non-negative on minimal free resolution. So original functional actually was non-negative on arbitrary resolution and certainly not good enough to prove the result. But this sort of uses minimal free resolutions. So now let's look what we can do with this. First, for the existence. There exists a zero-dimensional model with pure resolution for any degree sequence d0 up to dn plus 1. So this was proved by Eisenbart, Floyst, and Weyman in characteristic 0. And they have a different construction than in the paper of David and mine, which our construction works in every characteristic. Let me explain two, because it's so easy. I consider finite projection of Pm1 up to Pmk to n, where M1 up to Mk are the step sizes of the cohomology table. Remember, it was slowly going up, so we have sizes of steps. If it's always 1, then we have a product of P1, but it could go up further. Since the number of steps, of course, is the number of columns, number of rows which we had, right? So this is, so they sum up to n. So this, we certainly have a finite map to Pn of these. And now we just take sort of a line bundle on this product and push it down and take a suitable twist, and we will see that this will be a supernatural bundle just by König. So construction means that sort of in each twist there's at most one, for each degree there's at most one cohomology group Hi E of k non-zero. So if we, with König, we sort of certainly have a control. I mean, the individual terms here, there will be only 0 in 0 and M1, and you see we can do it.
Negative regularity? There's supernatural vector bundle has negative regularity.
Oh no, can have anything. I mean, you can, if you have a supernatural, a vector bundle, you twist it, it's still supernatural. You just shift the table a little bit. So here's now the proof of the Söderberg conjecture, which I guess it's not very enlightening, but I give you sort of nevertheless the basic fact. So we have this outer facet corresponding to f minus f and f plus. So we omitted f in the simplex. And then we look at the f at the twists which occur in all three sequences. So we admit two terms, the f tau and the f tau plus 1 term. So this is just the right number of terms for a degree sequence, z1 up to zn. And we take a supernatural vector bundle with that degree sequence, and then we take the truncation with tau, and c is f tau. And it turns out that this is going to be the facet equation. Let's talk about the analog for vector bundles and Cohen-Macaulay modules. So we had the vector bundle paired to Betti tables, or cohomology table paired to Betti tables, and we can use sort of the same equations to get information of the possible cohomology tables of vector bundle. And the analog is really the cohomology table of an arbitrary vector bundle on Pn is a positive linear combination, rational positive linear combination of cohomology tables of supernatural bundles. I think this is a rather interesting result. I wouldn't have dreamed about that. Now, Söderberg then did the non-Cohen-Macaulay case. It turns out that the inequalities which we provided were just fine, enough. We used enough of them. Now this is unbalanced situation. So we had Cohen-Macaulay modules or zero-dimensional modules corresponding to vector bundle. Now if we have arbitrary modules, what should we do? I guess that's sheaves. We should do something about sheaves. So the analog of the second result should be a theorem about sheaves. So we can speak about supernatural sheaves. I guess actually I defined that. So supernatural again means that for each twist only one hi of f of d is non-zero. And then super means that we have integral roots. Of course, if we have a torsion sheaf, so say a sheaf of dimension s, then there will be only s roots. And it will be convenient for us to put the further roots s1, s plus 1, s plus 2, I guess, and so on to minus infinity. Having done this, we can compare root sequences. And there we have a partial order. And I would like to denote by gamma z for root sequence the cohomology table which correspond to the sheaf which is this Hilbert function. So I take the degree of f to be s factorial. So now if z is an infinite set of zero sequences and qz is the sequence of numbers and gamma a cohomology table, we write that gamma is the sum of qz gamma z to mean that each entry of these gamma qz gamma I dz, each entry corresponds to the corresponding entry of the cohomology table. And here's the result which we hope to be able to write up before 2010. I think this is safe, pretty safe. That gamma f be a cohomology table for coherent sheaf on Pn. Then there is a unique zero sequence z, chain of zero sequences z, and a unique expression z in z of such sums, where the qz are positive rational numbers. So, yeah. I give you an example what the statement is. So here's the ideal sheaf of a point in P2, which is sort of the easiest non-vector bundle sheaf I could think of. The cohomology looked like this. So I dropped the zeros to make it more visible. So this 2, y2, well, we have three linear forms, 1 point, the two functions are left in the ideal, and so on. So then we can write this as gamma with some zero sequences, and zero sequences which occur here of the type 0 minus k, is just two numbers. And the q0 minus k are these rational numbers. So let's try to prove this. So we look at a supernatural sheaf which is the largest zero sequence with the same upper shape as a given sequence. So the upper shape, I guess, is sort of this piece here. And so that's this gamma 0 minus 2. And its cohomology is that. So this is a cotangent, but maybe twisted. And then we subtract. And we subtract so that the corner values, so these are the corners. The corner values after subtraction still stay non-negative. So if we want to do that, then we can subtract a third of this. Which makes a 0 over here, and then we get some fractions. Now, second step. Again, look at the upper part. So now this is a different vector bundle. And we want to subtract something like that. And you see the 4 compared to 1/3, that you can subtract a 12th of this. So And if you do that, then you got one more 0. And then we continue. So we do it again. What's the problem with this? You have to prove that all the entries stay positive throughout this process. Because I only looked at the corner values. And of course, all these inequalities which we had proven help for such a thing. Thank you.